implements the protocols with a lot more ease. And to answer this, like, I mean, there was one question in the previous session. It was about the real-time events, right? So definitely you need timers and interrupt handlers to take care of that. Okay. So in fact, most of the operating systems will have very powerful timer structures, because how long the packet can reside in the queue. I mean, at what time you will decide that you can discard the packet. At what time you will actually raise an alert to the higher layer. At what time you will say that there is an overflow situation or an underflow situation. So there are several events, and how do you really decide that? So certainly the timer connected with the protocols is going to be very powerful. So while actually timer is still important in the conventional operating system, but in networks, I would say the network operating systems cannot live without the timers, okay? Because each event is eventually driven by various timers that are set, for the protocols or the packets or for interfaces. If you look at it, they are all driven by timers, okay? So even in timers, you'll have different types of timers. One is, you can have a passive timers wherein you poll the code what you write will keep checking whether the timer is expired or not. You set the timer and you keep it expired, check for it. There are certain active timers where they will interrupt you saying that, hey, this is up, your time is up, now you have to take some decision, okay? So in fact, each packet, the moment they get in, they'll be assigned a timestamp saying that, hey, this is the time you got in, so that they are able to take a decision at what point of time I can actually, say that, okay, this is too long a time that this guy is living inside my system, so it's time that I dump him, right? So they're very important. And the interrupt handlers, they're very powerful because since it's real time, so the real time events always happen through interrupts, either a hardware interrupt or a software interrupt, right? So the moment the interrupts happen, whatever the job you have been doing, maybe you are constructing a routing table, or maybe you are checking a security aspect of one particular connection, whatever that you might be doing. So based on the priority, you should be able to go back to the interrupts and handle them, right? So these are some of the more primitives that are related to that. So having come so far, if you really look at it, the real trade-off, the real challenge here is this. At one end, we are talking about the network layers abstraction, right? Because you have multiple layers, each layer will be worried about its own job. Whereas on the other hand, you are actually expecting a line speed performance, right? Because each layer, even the zero copy is one such example, right? So let's say the physical layer gets this frame, but to the data link layer, should they copy it or should they share the data? How do they really share this information? Let's say the data link layer has to put it onto the network layer. But network layer, so certainly the layer approach works very well for accommodating different types of devices, different types of physical layers. It's basically to support a diversified system of network. That's agreed. However, the performance-wise, we are always expecting to achieve the line speed. This is a perfect kind of, I would say, a paradoxical requirement of network operating system design, right? Because let's say in the physical layer you have the data, and let's say the network layer is going to take some decision on this packet. So how this information is going to be passed? Are they going to be in the same shared memory? If they are going to be in the same shared memory, how well they are going to be, still maintaining the layer abstraction, or will the network layer get to know what's really happening on the physical layer? Should we really make it happen or should we not? So at one end, we want the layers to abstract them. At the other end, we want each layer should operate on the same data without actually making a copy of it. So this is one example of a perfect trade-off, right? So that actually opens up a lot of challenges as well as different ways in order to achieve this trade-off. Okay, so if I really summarize it, writing a network operating system or designing a network operating system fundamentally lies on this trade-off. So coming back to this, what's the one key principle that we need to follow? I would say those principles are some of the design considerations. However, at least in my experience, I've seen that there is no one single principle that fits all possible situations, because each network device has its own purpose and what it really wants to do. However, the design consideration, as I was explaining in the earlier slides, that it must actually do the entire thing at the line speed. In the sense, is it possible to devise a network operating system that supports the protocols and the networks in such a way that we don't drop any packet? In other words, there is no retransmission. If we keep that as a single goal and design an operating system, so definitely that's the motivation behind the whole thing. But however, it's not just one simple way to achieve that. It really requires it's a lot more intelligent algorithms, a lot more ways of designing data structures, and even a lot more support from the hardware. Like let's say if it is going to have multiprocessor environment, so how we are going to designate different processor for different planes, even that decision will make a lot more impact on your system. So this is where, if you really look at it, either commercial operating systems or whatever the open source operating systems, if you look at it, so they are all differentiating themselves at certain dimensions, but fundamentally their goal is the same. So can we really achieve the line speed? So that the dream of each one having an infinite notebook is made possible. Okay, so with this I conclude this session, and perhaps I